Right, ladies and gentlemen, radiation and matter, emission and absorption. What are the points we go through? First, we will talk about transitions in general. And what will be important for us is golden rule, semi-golden rule, with which we can compute the rates of the transitions. Then again, we are talking about radiation and matter, and it turns that matter can emit some radiation and also absorb some radiation. We will talk about emission, absorption, and we will keep the discussion in most general way. Just some levels in the matter, some quanta to be emitted or absorbed, right? Then we will talk about master equations, which are in fact classical equations, which deal with classical probabilities, and that will allow us to make sense of the rates. We will finish it by considering actually the origin of quantum mechanics in general. We will talk about equilibrium radiation, black body radiation. Good. Then we shall talk a little bit about interaction of charged particles, how precisely they emit this quanta in quantum mechanics. Right. After that, we know what to apply, what to put into golden rule, so we can talk about the transitions. A long version of this lecture contains consideration of atoms and blue glow, but usually I have to go pretty fast about these topics. They are now student presentations. One can find the files of these presentations if you want to have more information about this. But I could not skip the lasers, so I will talk a little bit about the lasers, how all this master equation stuff will apply in the context of lasers. All right, that's the plan for today. The lecture is important for homework, so I will release next homework package, despite the fact that you still have to handle the second one. But just to be consistent with the course program. Very good. So let us talk about golden rule. Fine. We will talk about transitions. In a strict quantum mechanical sense, there are no transitions. There are no transitions, and there is some evolution of wave function of very complex system. We humans see transitions, and it's convenient for us to talk about complex quantum dynamics in terms of transitions. So we have some simpler quantum system, and there is interaction, and this interaction will provide the transitions between two states, quantum states of this system, initial and final states. Right. Initial, the system is simple, and what provides transitions is interaction. So for us, a transition is a perturbation theory effect. right? Transitions are characterized by quantity, which is in English shortly called rate. It's kind of advantage of English language. Say in Dutch, there's no such word. And one should always talk about probability change per unit time, which is a bit long. So luckily we give this course in English. So the system is an initial state, and it can decay, can transit to some set of states. And the probability of this transition is proportional to time. And we want to compute the coefficient of the proportionality, which is rate. Good. Fermi-Golden rule. Interesting. What is interesting about Fermi-Golden rule is that it's not derived by Fermi or proposed by Fermi. It was just in the book of Fermi. Very good. Fermi was a great scientist anyhow, but well, we call it Fermi-Golden rule. So what is this? In the book, you can find the derivation, but let me just outline how logical it is and what are main consistencies. Let's see what we have here. First, we have a vector, 2 pi divided by h bar, not very important, just a vector. Then we will have, for each pair of initial and final states, we have a matrix element of perturbation. The matrix elements we have already, we looked at it. It's when we compute energies, for instance, in the framework of second order perturbation theory, we have squares of matrix elements. The same we have here. Between initial and final state. All right, matrix element squared. In addition to that, we have energy conservation. Indeed, the energy of the whole system is supposed to be conserved. So the energy of initial state and final state must be the same. And this delta function guarantees that. So there's no total energy change in the course of a transition. Yeah. But if we apply this formula to discrete states, it will not work. Why? Let me sketch initial state. Let me sketch some possible final states. And you see that if the state's discrete mostly, these energies do not match. All right. Suppose by some wonder, these energies do match, but then the rate is infinite because delta function is infinite. So for discrete states, this formula is truly meaningless. Right. To make it meaningful, one has to assume that the spectrum of final states is in fact continuous and replace summation by integration over some parameter. What could be energy of the states? In this case, the rate is final quantity, it's finite quantity, it's just given by integral, and it makes sense. All right, so what's important is the spectrum of final states must be continuous. Let us understand what happens in real systems. Happens, for instance, in an atom. Suppose we will have an atom in, there's a ground state and there's excited state in an atom. And initially, atom is an excited state. Yes, Ilse, delta is a Dirac delta function. It has dimension of inverse energy consistent with the definition of delta function. So suppose we have external excited state and the ground state, and okay, all right. We cannot organize this transition if we don't have anything to dump energy to. Fortunately, we have electromagnetic field, we have photons, which have continuous spectrum characterized by momentum. So initial state in this case is excited state and no photons. Final state is ground state and one of the final states, and a photon in one of the states with a given k. So there's a plenty of final states. They form continuous spectrum. That's why we have finite rate. All right. Good. That's about general things, about Fermi golden rule. We compute transition rates. Transitions are here in the picture because we are humans. We are not quantum beings. We see the world, we see the complex quantum dynamics of this world as a sequence of transitions. All right, let's do something. Yes, Jens, indeed, as I mentioned, energy must conserve. One cannot get energy from anywhere. The energy of the whole system must be the same in the beginning and the end of the transition. That's why we have this delta function. Strangely enough, I cannot. Oh, yeah. Now it works. Let us elaborate on this system. So we have, say, an atom of a more complex matter system, and we will consider the transition between two discrete states of the matter. All right, B is B is ground state, A is excited state. Right. In addition, we have photons. We have photons, and generally, a state of a photon is expressed with occupation numbers, right? Occupation numbers for any given photon state. All right, let me talk about some general interaction Hamiltonian. How it is made. All right, it is made from some operators, sum over A. And for each A, we have a pair of operators. Operator X is dealing only with photons, and it's a superposition of creation and annihilation operators. That's a standard form for a field operator of the photons. Could be electric field, could be magnetic field, not really important in this class. While operator M, as its notation says, is totally about matter. It has matrix elements only between the states of matter. Good. And let us look at the processes which involve excitation of a certain photon. All right. And we will look at the processes involving this certain photon. We don't care about all other photons. They are just spectators in this transition. Their numbers do not change, so they are irrelevant. Right, let us see what do we have. For this particular photon, there are processes of absorption and emission. Let us see if I put all arrows correctly. Absorption. So initial state, there is some number of photons. And in final state, we have one photon less. All right, so we get energy h omega bar from the system of photons. And with this, we can rise the energy of the system. So it goes from B to A. This is absorption. There is a reverse process, which is emission. And what do we have now? We have n plus 1 photons in the final state. So that can proceed even if we don't have photons initially. Yes, Yunse, it is so that we always talk about the total system. The transitions will occur in a subset of a system, say for an atom in environment, but we consider the whole system atom plus environment, plus all the photons. As we see, we operate with wave functions, which are the functions of the whole system. Very good. Emission, absorption, and what we do now, we just compute the rates of emission and absorption and eventually compare them. All right. Good. It is a bit boring calculation, but pretty straightforward. So what we want to do is to compute matrix elements to square it afterwards. Fine, what we do, since operator X act on photons only and operators B on a matter, we can separate matrix elements as it's written here. All right. Then we compute we substitute expression for operator x, and we have some coefficient here, which comes from matter, and coefficients x in field operators. What's important for me is this term. Here I skip all creation operators in field operator x. Why is it so? Because the state, I have less photons in the final state, so I have to annihilate, not create. So I keep only annihilation operator. And finally, we could apply the formula. We have started second quantization lectures for matrix element of this operator, which happens to be a square root. A little bit ugly, but anyhow, we square it. So what we have, absorption rate proportional to the number of photons. The same we can do with emission rate, which is formally different process, different calculation, but it goes in very similar ways. We separate the operators. We leave only annihilation operators because we have to, oh, there's plus here. We have to rise the photons. So we end up with this expression. Again, we will use the definition of creation operator. Good. We have nk plus 1 coming with the same coefficient. So we understand that there must be some relation between absorption and emission rates, whatever the total rate, whatever this coefficient is. Right, let us concentrate on this. First, we talk about partial rates, and those are rates from to or from a certain state of a photon, certain k. Right, so we can write them like this. There is a relation between these rates. One comes with n, and other comes with 1 plus n. Right. It is a partial rate, so there is a delta function appearing here. Don't forget about the delta function, which guarantees energy conservation. Good. Then we need to compute full rate, which means that we integrate over all case, over all case, in this case. Good. So we have absorption and emission where n bar is an average photon number at a certain frequency, certain energy. And if this occupation number depends on energy only, like in the state of thermal equilibrium, that's what we have. So the ratio between the emission and absorption rate is given by average number of photons in the states with the energy corresponding to transition energy. Good. That brings us to this transparency, a very short one, when we summarize everything. Fine, absorption, logical or not, is proportional to the number of photons. Emission is 1 plus this number. This is natural because there can be also emission without any photons present. For some reasons, people prefer to separate these two terms, which is rather artificial. People talk about spontaneous emission, which can go with without photons, and stimulated emission. It is important to recognize that the presence of photons eventually stimulates the emission, simulates the transitions from the upper state to down state in the matter. All right, that's what I want to say. Let us see how to deal with this state, with these rates, how to describe what is going on using the picture of rates. As I have already mentioned, perhaps a bit explicitly, when we're doing so, we kind of betray quantum mechanics. And the equations which are right, master equations, it is in fact classical equations. They go about classical probabilities to be in a certain quantum state. So it's not exact, but it is pretty fine to implement it for the description of transitions. So let us first look at the matter which is in the states of A and B, master equation 1. Right, it's eventually just a balance. We consider transitions from state A or from state B. So, as promised, rates give you probability of change of probability to be there per unit time. So, if it goes to B, then the corresponding probability is smaller. Probability to be in the states, state A is smaller. It comes with minus sign. And it's also proportional to probability to be here in the initial state. So there is a kind of outgoing term. Expanse term. And there's also income term. Right, initially, the system is a state B, which is manifested by this factor, proportional to probability B, and there is a corresponding rate. Good. This equation must be foolproof. How can I check simply whether the equation is written correctly? Any suggestions? So there are two equations. Could be sign mistakes in the coefficients. How can I check if it is correct? Well, we have two states in our scheme, A and B. which means that the sum of two probabilities is one, precisely. Good. Time derivative of 1 is 0. That's why if we add these two contributions, we should get 0. Total probability should conserve. Let us see that this term, if we sum it up, this term cancels this term cancels this term, so it is okay. Fine. Master equation should conserve the total probability, of course. Good, that it's about the matter. Yes, you're right. In this case, A is ground state. Yes, you're right. Who is right? Sarah Sechan are right. Good. That's about matter. About the photons. Within each mode, within each mode with a given K, we have transitions which change the state of the mode, the number of photons in the mode. So we can write master equation for the probability to have a certain number of photons. Okay, it is made in a similar way. Let us see. There are terms with minus sign, which means that I can go from a state N to either with emission or absorption. And there are two terms corresponding to emission and absorption. Sorry, this is emission, this is absorption. Alternatively, I can initially be either in this state or in this state and come to the state N. All right, we also have here emission and absorption rates. What is important for me is that it kind of should correspond to the state, to the initial state. That's why we have N here for the emission and N+1 for absorption. Fine, so two master equations. One defines the states of the matter, and another one checks the probability of photon distribution within each mode. Right, good. Let us talk about equilibrium radiation. It is important to understand in this context. So let us assume that matter is in thermodynamic equilibrium. What does it mean? It means that probabilities to be in the states A and B are not arbitrary. They do depend on energy of the states A and B. And these probabilities are given by corresponding Boltzmann weights. Okay, there's some coefficient in front of this weight, which depends on full probability. I don't care about this. I'd rather talk about the ratio of these two probabilities. And in this case, I'm pretty certain it is given by energy difference between the states and temperature. Good. Let us see. Matter radiation equilibrium. What I can get from master equation 1? I can get this. How? To be on the safe side, let me take it here. All right, so it's equilibrium. So I put this to 0. I get it to this term to the left side. And well, I divide this. I divide this by PB and by this factor, so that's what I get. So the ratio between ratio of probabilities is a ratio between emission absorption rate. Okay, that's what I get from the fact that matter is in thermal equilibrium. That, by virtue of energy conservation, gives me that the ratio of these two depends on the frequency of the photon. And this is, as we discussed, the ratio of the rates, emission absorption rates, is like this. So what I can conclude from this, I can compute what is average occupation number. Not to be surprised, it corresponds to Bose distribution, to standard Bose distribution for bosons at finite temperature. That's one of the ways to compute this occupation number. Just assuming that the matter is in thermal equilibrium. Let us see. We can also compute the number of we can also implement equation 2 and compute the average number of, the probability to be to be sorry, I guess it's a short time for break. We look at master equation 2. under same conditions, assuming there's matter in thermal equilibrium. What we can do about this? We can compute the probability to have n photons in this weight. How we can do with this master equation? We can have a balance between the states with n and n plus 1, right? And then the ratio of these probabilities, yeah, can be obtained by from comparing emission and absorption rates. And in fact, it corresponds to the ratio of probabilities to be in the states A and B, which is given by Boltzmann factor. From this, we can compute the total probability to be in the state N. Not surprisingly, you immediately see Boltzmann factors, and this is the normalization. Boltzmann distribution we have. Let us see. I think I want you to do some Planck and Stefan stuff, but let me just do it after the break. So I will. It is good now. Right. I'd like to finish this discussion about master equations, thermal equilibrium, with famous derivation, which actually gave origin to quantum mechanics. Everything came about this simple calculation. And this is about computing the flux of irradiation in equilibrium. So how does it work? So suppose we have a body, black body, or I have to use black color, black body. From the left side, which has a temperature T. And it emits photons to the left. Let us see, they can come with all momenta, but it should, all these photons should go to the right. Okay. So now I can try to compute the flux. The flux is contributed by fluxes, flux in that direction. For each individual state at each k, we have this formula. We sum up over all k. This takes care of the fact that we look only at photons going to the right. And this is the average occupation number of photons at given energy. Fine. What we can do this with this integral, we can transform it, and to get from integration over k to integration over frequency. And that's what we have. So here there must be Poisson distribution, which eventually drops at high frequency. So there is no chance to emit a photon at high frequency because there are none. However, if one gets rid of certain theta here and everywhere is a heaviside theta function. So theta of x equals 1 if x is bigger than 0 and 0 otherwise. This is the definition of theta function, heaviside theta function. Fine. Now let me compare it with a classical approximation of this NB, and that will be so if there is no quantum mechanics, this is what we have. To show the difference, I plotted. This is Stefan, classical expression for radiation emission as a function frequency. Here's what Planck gives us, and this is actually distribution of flux for black body radiation. If there is no quantum mechanics, we've got immediate and fortunately very solvable problem. If there is no quantum mechanics, this integral diverges, which means the flux from any warm body is infinite. So all temperature of matter would go into radiation immediately, and all stars, including our sun, would shine just for a split of second, and they will be dead with all of us. So this is how Planck constant saves us from this kind of shining death. All right, that's what I wanted to talk about Planck and Stefan. And as you remember, it was an attempt of Planck to resolve this paradox in some phenomenological way, which eventually led us to quantum mechanics. Good. Let me talk about radiation, about interaction of matter and radiation. And let me describe a trick of derivation of this interaction, which is based on something we have discussed for the fields. And it's very important in the context, whatever, of our road, cosmology, general physics, that this gauge transform also has a counterpart in transformation of wave functions. Namely, there is a gauge transformation of a wave function, which is which corresponds to multiplying this wave function on by some phase vector with some phase. I fancy to have electric charge in front of this, but it's just a vector. So I multiply wave function with some phase vector. And okay, this is gauge transformation. If I write the equation, Schrödinger equation for this transformed wave function, it will differ from the standard Schrödinger equation. Right? For instance, if we differentiate it with respect to t, which is left side of Schrödinger equation, we differentiate this term, and this is fine. But we also differentiate this term, and that gives you extra factor on the left side. The same will happen if we apply derivatives to the transformed wave function. Good. So what we get now is a modified Schrödinger equation. Right. And now this identification, we associate this transformation of wave function, which is about matter, with a gauge transformation of the fields. So what to observe is that A eventually always comes with gradient of phase, and phi comes with time derivative. So that gives me an idea that I have to put phi here and A here, right? That makes it this gauge trick. Indeed, we do a kind of a round substitution, heuristic substitution to this equation. We put A here, we put scalar potential here. To come to the correct equation, which will include also electromagnetic fields. As you see that scalar potential comes with time derivative, and vector potential always comes with x derivative. Sorry, with a coordinate derivative, vector x, y, z. One talks about derivative elongation. So any derivative either with respect to coordinate or time in the presence of electromagnetic field gets elongated, gets an addition proportional to either vector potential or to scalar potential. All right, that's the way to derive interaction between particles and fields. Gauge transformation. Right. We need to do several things before we make it practical. Okay. First of all, we need to promote this to go to second quantization. We need to replace wave functions by field operators of particles. That we do. And we need to promote fields into operators as well. So they become not classical fields, but rather operators quantities. Then there is yet another, well, a bit artificial separation, which is motivated by the fact that we are in non-relativistic world, and some of the gauge choices are more convenient for us. And it is sarcasm as to use Coulomb gauge and instead of operating with scalar potential, just replace it with the effect of this potential. And what is the effect of this potential is an instant interaction between particles. So instead of writing phi here, we just put the interaction term we have been dealing with. To forget, that allows us to forget that Coulomb interaction also comes about photon exchange, which is perhaps a nice concept, but it's very inconvenient to think about it all the time. Right, with this, we can achieve the following separation. So non-interacting particles go here, terms with phi, they become interaction, and they also attributed to matter. We have Hamiltonian radiation, which is usual Hamiltonian we derive, non-interacting photons. And the interaction actually comes from this term. So interaction of matter and radiation is interaction with vector potential. Fine, let us zoom at this interaction term. Let us neglect for second order corrections, which are usually not relevant, which can in fact be reduced to first order corrections. And let us look at the answer. The answer is eventually simple. Perturbation Hamiltonian, which settles interaction between particles and fields, has the following form. It is a vector potential, which is an operator in terms of creation and annihilation operators of photons, and current density, operator of current density, which, as we see from the definition, contains field operators of the matter. So it's something which characterizes matter. Well, what I put here is a non-relativistic form of this operator. I could also write a relativistic form. It's a bit more complicated, and we are, as I said, in non-relativistic words, or I keep just current density. Right. If I go back from second quantization to individual particles, well, I can transform this formula in the following way. So it's a summation of all particles. Each particle has velocity, which contributes to the current density, all right, at the point of the coordinate of these particles. So it's all consistent. It's really operator of current density, and this is interaction between field and matter. Fine. Let's see. Now we shall look at applications, so to say. And as I promised in the beginning, I perhaps don't have enough time to go through all applications in detail. So let me go through atoms and through Cherenkov radiation in a very fast tempo. So just for illustration, not for learning. Right. Let's talk about atoms, spontaneous emission by atoms. This is an early observation, spectral lines, which eventually was another big impetus for creation of quantum mechanics. Thin lines corresponding to atomic transitions. And excuse me for doing that, but general physics is very important. So simultaneously, I'm gonna run a quick test about sorry, was distracted. There's so many very critical things going on. Quick test on general physics. Sun, the sun of a star, is can consist of atoms, some hydrogen and helium atoms, with a bit of other elements. Atoms emit, since the states in the atoms are discrete, they emit at certain frequencies, which you can see as spectral lines. So if one considers hot gas, you see these lines of different color corresponding to different atomic transitions. Well, since the sun consists of atoms, one expects this spectrum coming from the sun. In fact, this is actual spectrum. So the spectral lines are eventually black, no emission. And there is a continuous spectrum from our favorite star, from the sun. So who can explain this inconsistency? Just write something to the chat or speak up. All right, so sure. That's fine. Black body radiation has continuous spectrum, and somehow mine is the transition energies. But for me, the paradox is as follows. The sun consists of atoms. Atoms emit only in lines. So how the continuous spectrum comes about? Here, good, Francesca. It is to kind of reasoning to correct sides, multiple scattering events with other particles. Yeah. Atoms have thermal energies, but they still kind of discrete states, so they emit discretely. So the answer is that the sun consists of atoms. That's fine. It doesn't consist of independent atoms. In fact, the atoms, which are actually hot and emit radiation, which we see, are in plasma. They interact much with each other, and their states, in fact, form continuous spectrum. And there is emission from this continuous spectrum. That's right. But if we go a little bit farther off, farther from the star, by continuity, we have some remains of a sun atmosphere, where atoms are independent owing to big distances between them. And this part of sun absorbs radiation. That's why the lines are eventually black. So we don't see continuous spectrum because most of it is absorbed by individual atoms, called atoms around the sun. Good, we have sorted this. So we can forget about this. We can concentrate on atoms, and we can compute the rates of this transition. So how do this? No photons around, just spontaneous emission. Transition rate is given by this expression. Here we need to substitute our what we have derived recently. Interaction between matter radiation. We have to take care of energy conservation. So the difference between atomic states should match the energy of a photon which you emit. So initial state, final state is just with one extra photon. Right. What is interesting and important to know about atoms is that dipole approximation works there. And we can eventually replace the vector potential in this Hamiltonian, which eventually depends on coordinates, by its value precisely at atomic position. In other words, the vector potential varies slow at atomic scale. But this is what we kind of have feeling for. variation of atomic potential corresponds to wavelengths of the emitted radiation. And for atomic scale, it's something like 500 nanometers, while the size of the atom is only 0.1 nanometer. Right, we need to compute the matrix element of velocity for each particle, current density. It's good to play a trick with this operator and say that it's actually velocity, and velocity by virtue of Heisenberg relation is a commutator of coordinate and Hamiltonian. So one can express this matrix element in terms of matrix element of dipole moment between those states. That's why it is called dipole approximation. So in fact, for emission, we need to know the matrix element of dipole moment between two states. Right, so let us have it here. This is our estimation of the square of matrix elements. Here's a matrix element of dipole interaction. And this comes from arc the square root, which is here, which is in the definition of field operators. Fine. Then we important moment we need to make sense of these delta functions. To this end, let us compute the rate in the interval of solid angle in a certain direction. So in these directions, there can be photons going with different Ks, but only those which satisfy energy conservation actually come into play. All right. So this is a partial rate to a state with a given Q. We need to integrate it over Q. Right? Fine. We replace this three-dimensional integration by integration over modulus Q and solid angle. And we integrate Q, and that kills this delta function. It makes it finite. So we come up with definite answer. I do presume that you remember how to integrate delta functions. Right, so there's already finite rate. We need to integrate it over solid angle. And in this case, it is important, the direction of polarization is important. Right, let me talk a little bit about this. Let me define the polarization vectors for any Q in the following way. We have the vector of dipole moment, and one of the polarization vectors will be perpendicular to both propagation direction and vector of dipole moment. And in this direction, we don't have any radiation. All radiation will go to this vector, which is perpendicular to Q as it should be and lies in the same plane as the vector of dipole matrix elements. Good. Implementing this, we obtain that the intensity of irradiation given the direction of dipole moment is just given by this vector. Here I sketch it, intensity diagram. No emission right in the direction of dipole moment, maximum emission in the direction perpendicular to this dipole moment. Fine. Then we can integrate overall rate, basically integrating this sine of f. That's what we get. Right. We find here an alt-equidistance of R's. We find here fine structure constant. So this rate is proportional to a small dimensions quantity, fine structure constant. Well, it has also dipole or moment matrix element of dipole moment. It has some dependence on frequency of the photon emitted. Let me just give the estimation. And what is important to me, well, let us first define a quantity which is can be estimated easily. I will compare the rate and frequency, emission frequency. If I consider the level, the difference of, if I consider two states as a kind of oscillator, the decay rate will give me inverse quality factor of this oscillator. Right, so I run this estimation. There is a small constant alpha. That's one thing which makes it small. Another thing is the fact that dipole moment in atoms, which is of the order of atomic distance, is much smaller than the wavelengths. So we have the ratio, which justifies dipole approximation. We have the small number atomic scale divided by wavelengths, all squared. In total, if we express this ratio in terms of alpha, we have alpha to the cube. Alpha is 10 to the minus 2. So we obtain that these rates are kind of million times smaller than the frequency corresponding to the energy difference between the rates. For large dipoles, the rate could be bigger, but it still will be of the order of alpha. Right, I have to switch to lasers. So let me skip some symmetry elements, selection rules. Let me skip illustration for hydrogen atom, which we really can come with a number. Let me skip about Cherenkov. There will be presentation soon. Let me, as I said, talk about lasers. The lasers, a rough cartoon of the laser is stimulated emission. Kind of the cartoon is that we have some atoms in the excited state. And first atom emits a photon. So there will be 2 photons. Next atom will see 2 photons. And it will emit next photon much faster because of stimulated emission. And it goes on and on, more atoms switch off, and that increases the probability for next atoms to go off. It is very rough cartoon. If you look at the equations, you hardly see anything from the cartoon except stimulated emission, of course. But this cartoon is important because it gives main technical requirements to the laser. To make use of the lasers, we should first keep the atoms excited. That can be done by providing some energy to the atoms, like for instance here in helium-9 on laser, it's electric discharge which is going on here. And we need to keep photons in the laser, because if they go off the laser, they won't interact with atoms, there will be no stimulated emission. Here in this particular setup, it is provided by mirrors. Have to make a different count. By mirrors at the end of this, at the ends of these tubes. So photons, and in this case, as we see, laser light correspond to green photons. While for this particular laser, we have a lot more of non-lasing radiations, which come because of this discharge. Good, it's cartoon. Let's make it a little bit more consistent. This charge excites the atoms at a certain rate, number of atoms per second. So it's about excitation of helium atoms. They got excited and they collide with 9 atoms, and thereby they put 9 atoms into excited state. Then these atoms emit, and they can emit to, well, just out of the laser. That's what we see, that orange light. But they also can emit to a single mode. Look, here it emits to a zillion of modes. Here it emits to a certain mode, which is called lasing mode. But if there are sufficient number of photons in this mode, these rates can become comparable. That's how the laser works. And again, to achieve this great population, one has to keep somehow these photons, green photons in the laser, for instance, by means of mirror. But with this, we can already write a more useful equation. This is for a number of excited atoms. So what does it do? It has income term. It has non-lasing emission. So atoms just go to ground state, they're not excited anymore. And it has emission into this lasing mode. So we need to know how many photons are there in this mode. Okay. It is excitation, it adds photons. And there's also escape of the photons in this mode from the laser. Okay, this is a kind of, we need only these two equations to describe laser, but we also can look at the distribution of photons, probability to have certain photons in this particular mode. Okay, let us in remaining minutes talk about first two equations. Okay, what can I do with this? It's quick to solve these equations in the station case, so that we have a number of excited electrons in terms of number of photons. And that is emission, total emission into the lasing mode. And as you see, it should be always smaller than the rate with which we excite atoms. So the lasers in this model would eventually saturate a big number of photons. Right, because it cannot emit more energy than it is supplied by excited atoms. Right, this has to be compared. The gain of the laser has to be compared with a number of quality factor of the lasing mode, with the fact that photons are lost from the mode. So this gives you a line in this plot, and you see if dissipation is too big. There is no solution, there's only solution without photons. But if we increase quality factor, if you make it smaller, there is a crossing point into plots which corresponds to certain big number of photons in the laser, so it can be saturated. Good, that's how the lasers work. It is important here that emission is stimulated. Again, it looks almost as magic. So too many modes to emit. There's a particular one at which we can concentrate, and the emission to this mode works if there are the sufficient number of photons in this mode, stimulated emission. Good. In the remaining minute, I would like to assess photon distribution in a laser. Right, we can imply master equation number one. For simplicity, I assume that the laser is almost saturated. Again, I can solve this equation like we did for matter radiation. Just consider the balance of emission absorption at given n. That finally gives us probability to have a certain number of n, which happens to be Poisson distribution. And here we have parameter, which is average number of particles in the photons in the laser mode, which is usually enormous. So let me plot it. That's Poisson distribution for a rather big number of photons in the laser 300. You see that this is not thermal distribution. It differs quite a bit from this. It's concentrated in a given number of photons, but still it has a spread which is proportional to the number of photons. So it looks like that our laser has spread of a number of photons, and it looks like the number of photons fluctuates in the laser. That's what we concluded. And to give kind of more motivation for the next lecture, in the next lecture on Monday, we will learn that it's absolutely not so. The fluctuations in the laser are not the number of, do not correspond to fluctuations of number of photons. Fluctuations in the laser are different. And this calculation, or in more precise terms, a conclusion from this calculation is not correct. Good. So next lecture will be about coherent state, which has something to do with lasers. With this, let me stop the recording.